we continue with the Submodule 4.2 techniques for site characterization of groundwater heat pumps. So what we discussed before is that we need the aquifer thickness, hydraulic gradients, hydraulic conductivity to assess how much water can we pump out. But we said, okay, this water carries heat because it has a specific heat capacity that we can store heat. But of course, what is important also is the temperature of the groundwater. Because if the groundwater is too cold, for example, then we cannot use that for heating. This can happen if you are near the Alps, for example, and you're near a river or whatever, then the river inflows directly in the groundwater body and in the aquifer, and then actually could be quite cold, so 5-6 degrees Celsius, and then you can not use it so much for heating if you have a limitation, for example, for your heat pump. So sometimes there are some technical limitations. You cannot go on -3 or 0 or 3. And then there is some limitation. You cannot use so much temperature. You can just actually reduce the temperature here by 2 Kelvin and not by 6 or more Kelvin, for example. Also, it is good to know if the groundwater is too hot and you want to use it for cooling, for example. So if you use it to cool your house, then you need a cool temperature, of course. Then it's quite favorable in summertime. And if you have a groundwater temperature of 16 or more, then actually maybe it's not favorable for cooling anymore, because there are also some regulation limitations that, for example, in some cases, you cannot re-inject the groundwater if the temperature is higher than 20 or 25 degrees or whatever. So it's not allowed. So this limits also the use. So at the end, it is very important to know what is the groundwater temperature. And of course, the groundwater temperature you can measure again. So with the more or less the same devices as you use for to measure the groundwater head. There are some temperature sensors in some devices, and then you can measure the temperature. You have to know that the temperature in the groundwater body is not totally equal over depths. So you have a higher variation. If you are in shallower parts, then it's getting stable more or less if you go deeper somehow. But of course, here you see an example from the case study of Munich, where we measured the heat, the temperature, and you see that in the middle of the city we have a higher temperature as in some surroundings. This is depending on we have a lot more ceilings in the city center, so the temperature is then actually increasing, and also we have a lower aquifer thickness. This makes it also quite very sensitive to groundwater, to temperature changes. Where we have a higher amount of water and a higher volume, actually the groundwater temperature stays a lot more stable. Depends, of course, also on the depths to the surface. So temperature measurements are quite important, and also to consider what is the initial temperature and what can I re-inject, what is allowed and what is technical useful. Of course, there are other things what you have to consider by using groundwater heat pumps and also installing a well. This is, of course, what is the hydrochemistry of your water. So hydrochemical aspects are good to know, because we have some iron clocking effects. For example, you can have some scaling. So if you have a lot of carbonate in your water and then you change temperature, then the carbonate balance is changing, and then you can have some scaling, what you see in some of those pictures at the top. And then the productivity of your well is reducing, and this could lead to that your groundwater heat pump is not working anymore. So it is very good to know what is the hydrochemistry, and in some benchmarks, some thresholds told you that's maybe not useful for groundwater heat pumps if you have, for example, too high concentration of iron and manganese, then this leads to some clogging effects of the well. And there are some technical methodologies to and workflows which can actually overcome this barrier, but in general you have to be very careful, and so it is quite very recommended to do a hydrochemistry analysis before using the groundwater heat pumps. Of course, so unfavorable conditions for groundwater heat pump systems, as you can see here, is acid, carbon dioxide rich, low mineralized, chloride rich groundwater. So you have corrosion effects or blocking effects if you have suspended particles. And as I said before, iron manganese can be a problem. So important is the tightness of the system, of your well system. Normally, if you do not have a lot of leakage or whatever, if it's very tight, you do not have a big problem, but it is you have to control it and to see how that works, of course. So besides that, there's also another aspect. This is, we talked about groundwater thickness and that we should measure it and that we should define it. Well, of course, what we see is groundwater is dynamic, so it's not static. It's changing. The groundwater table is changing because you have changes of the recharge, you have changes of precipitation, and so that we have changes of recharge, and this leads to dynamic in the groundwater table. So for the planning of groundwater heat pumps, it's important to have that in mind, to see, okay, my planning basis should be actually low level of the groundwater head. So because you have to make sure that enough water is available, especially in the heating or cooling season, whatever you're using for your groundwater heat pump system. So also the planning base should be the low level of your groundwater head. And this is, you have to analyze some groundwater time series for that one, and also having in mind some prognoses to the future, because our climate change changes, unfortunately, also our groundwater table. And normally, if you have enough groundwater available, it's not so sensitive, but you have to be aware of. So for if you plan your with low level groundwater tables and groundwater measurements, then you're on the safe side.